All right, to sort of cap off our discussions about spin and polarization, I'm going to give an example of something these can be used for. And it's maybe something you've heard of, quantum cryptography. And so cryptography in general is is often something like this. So this is a particular type called using a symmetric key, but it's somewhat illustrative of cryptography in general. So you start with your plain text. So this is maybe whatever you want to send to your friend. And then when you click send, something will encrypt it, turning it into this sort of indecipherable sort of looking thing, and it's encrypted using this key. And then when your friend uh, gets it, when they receive the message, they will use that same key to decrypt it. So there is an asymmetric version where there is a public key to encrypt it and then a private key to decrypt it. But I'm going to use the symmetric key version here to illustrate this. And so when you encrypt something, the key is sort of what's telling you how to translate it from plain text into the indecipherable text. And then you can use that same key to turn it from indecipherable back to decipherable. And so a very simple version of a key would be something like move all letters right by 3. And so that would mean if you have the letter A in your plain text, that would then be translated to, so you would have A, B, C, and then D. So it was moved 1, 2, 3 to the right. So this becomes a D. And then if you had, say, a B, that would get turned into an E, and so on and so forth, so that everything's turned to the right, and eventually you get back around, and this will be X, Y, and Z after you move around the entire alphabet. So that's a very sort of simple case of what an encryption would be, but in this case, the key would be this. And so you would type your message, it would shift all the letters to the right by 3, so that you would have just what would look like a jumble of letters here. Then your friend would receive it, and they have the key, so they could their key could tell it to move everything back to the left by 3, and that would turn it back into plain text. Well, with encryption in computers, they use a little bit more sophisticated uh, uh, procedures, sophisticated strategies for this. But for our purposes, I just wanted to point out what a key might look like. And so you can kind of see the problem here is that you and your friend both need the same key. If your friend doesn't have the same key, then they wouldn't be able to translate it back into plain text. And so, one way to solve this problem, obviously, is just for two people to come together and just say, this is going to be the key. So, yeah, just use that key, and then when I send you a message, just use that key to decrypt it. And another way, which is less secure, so you could have the two people sort of come together face to face, or you could have them communicate it over their communications. But then, obviously, this is then subject to interceptions. There might be some other person here that taps into it or receives your signal at the same time, and so forth. And so we will call this Alice, Bob, and Eve. Eve often added into the regular Alice and Bob, meaning eavesdropper. I think this is how you spell it, eavesdropper. But that's what Eve means is eavesdropper. And so what we want to do is actually use quantum entanglement to actually make sure that if somebody is eavesdropping, then we know that they are eavesdropping. And so for that, what we can do, so what you do is you actually, so we have Alice over here. So Alice, and she wants to send the key to Bob, who's over here. And so what she will do is she will polarize some light here. So she's going to use polarized light. And then she will send it randomly through a polarizer. So it'll either be a polarizer oriented this way or a polarizer oriented this way. So if she sends it through here, then when it comes out of there, it will still be polarized up because this has that vertical on it. And so then it can come over to Bob, and he will have his own polarizer over here. So if he's using this one, then he will detect it as being an up. Whereas if it goes down here, if Alice's computer randomly selects this to be the basis, then what can happen is what comes out of here, it can either be polarized that way or that way. And so when it comes over here to Bob, where he is still using this same basis here for his polarizer, and then what can happen is he can get one of two different things here. So one half of the time it will be up and one half of the time it will be down, because he is sending something that is oriented either this way or this way through something oriented this way. And so we know that there is that angle here between them, and that is going to affect the way that his polarization comes through. And this can also be done sort of in the reverse way, where if we have Alice over here, she sends it through, say, this one, and it comes out still like this, then it could either go into Bob's, which is like this, or it could go into Bob's, which is like this. And if it's like this, then it will be up all the time. When it's like this, it will be one half up and one half down. And so you end up getting sort of the same thing going on here. But whenever Alice is sending one of these photons, she is randomly choosing one of these bases here, and Bob is randomly choosing bases here. And so only some of them will end up being in the same orientation. So when Alice sends it this way, only sometimes will it end up just sort of going all the way through like this, or like this, where everybody has the exact same thing. So over here is just a look at these different bases. So I had the rectilinear and the diagonal bases here, and then we can look at this table right here and see that this is how Alice prepares her photon. So 0 being to the right and 1 being up. Actually, no, I think that was the other way around. I think 0 is up and 1 is to the right. And I think that's usually when you are using quantum computing, often how it is. I mean, it's just kind of convention to call it that, but this is, I think, the usual way to do it. But when we see here, if Alice prepares in 0, she sends it through the rectilinear. That'll stay polarized up. Bob uses the rectilinear to receive it. It's still up. He gets a 0. Then we see the same thing. If everything is the same all the way down, he gets a 1, a 0, and a 1. and they throw out everything that is not the same. So I guess I should mention too that after they send all these things, and usually you'd want to send a whole bunch of them, you would want a really, really long line of zeros, ones, and zeros, and all that randomness going on with that. And so you'd want something like this that's, probably hundreds of digits long. Maybe even longer since you have to throw some of them out. So you get these random zeros and ones because it's based on the randomness of which basis is chosen. But then Alice can even over an insecure line tell Bob which basis she used for each of these, and then Bob can tell Alice the bases he used for receiving them. And so they can filter everything out. I think that they call it sifting. I think it's called sifting. And so they end up using only the zeros, and ones for the ones they agreed with. And so we see that they, like I said, these can be insecure because the idea is that they don't know what the actual polarization was. They only know the bases. But we can imagine that when we're sending these photons across our I guess quantum communication network, that once again we have Alice here sending those photons to Bob, that we also have Eve up here who might also be receiving these. But what we can do, since these photons since these photons moving across will have a particular set of superpositions, if Eve actually listens in on it, if Eve intercepts them before Bob gets it, she will then have to send another one to Bob, and this one will not end up going to Bob. And so with the quantum encryption, we can actually tell if Eve is receiving this before she sends one to Bob. And there is something called the no cloning theorem. I was going to go through the whole no cloning theorem. I mean, it's not that complicated, but there's just kind of a lot of steps. But I think I'm going to keep this one a little bit shorter. But it essentially is just telling you that if Eve is intercepting the photon and sending another one to Bob, she doesn't know what to send to Bob. And so if Eve is eavesdropping, she measures and then sends the new unentangled photon, which will be wrong 50% of the time. And so we can imagine, so we see up here we have 0, 1, 0, 1, that's 4 of them. Then we have 1, 2, 3, 4 that are blank. And so when we have no eavesdropping, 1/2 of these will be correct between Alice and Bob. Whereas with Eve, since she is receiving this 1/2 and then reducing it by another 50%, only 1/4 of them would be correct. And so what Alice and Bob can do is they can look at how many of these they had correct. So how many of their giant string of zeros and ones. So take the correct ones and divide it by the number of total ones. And then that should be 50%. That should be 1/2. And if unless somebody is listening in, because then, as I said, they can't clone the signal. They can't clone the state of the photon. So they'll just be sending one that could be half the time it could be right, and half the time it could be right, and half the time it could be wrong. And so that one half, as I said, is reduced down to 1/4. So if Alice and Bob see that they're only agreeing on these 1/4 of the time rather than one half, then they can then they know they're being listened to, and they can just sort of scrap the whole thing and then maybe change to a different frequency to try sending their keys to each other. They can redo that until they find out that they are not being listened into by Eve. So yeah, if you are interested in why Eve can't send the same thing that Alice sent to Bob, then look into the no cloning theorem, and that is the reason why Eve cannot send the same signal to Bob that Alice did. But the outcome is, like I've been sort of repeating, I guess, that if nobody's listening, then half of these will be correct. If somebody is listening, then only a quarter of them will be. And so that is a way you can detect if somebody is listening in, and that is how you can make sure that you have a secure key, by only using a key that was sent when half of the things were, when half of the string of numbers were matched between the person sending and the person receiving. Anyway, that is it for this video, and unless something else occurs to me, I think that's going to be sort of the end of the quantum mechanics videos on spin. So you may have noticed I put the time evolution operator, which allows us to get the time-dependent Schrodinger equation, in the previous video. And the reason I did that is because if I did the no cloning theorem, then we would be using the time evolution operator. But since I didn't go through that here, then that didn't pop up. But anyway, like I said, I think this is going to probably be the last one I do on spin. After this, I will be talking a lot more about the Schrodinger equation, and I will be showing sort of how to derive that. So it's going to be a derivation from classical mechanics, and so that's sort of that's why I put it in the scare quotes here, because it's not like a true derivation, but we will see our Hamiltonian operator popping up. I showed how that sort of fell out of the time evolution operators in the previous video. We will see our momentum operator showing up. So these two are kind of big ones here. And just as sort of a little trivia, this is energy, which is related to the symmetry that is time symmetry. So if you've ever heard of Noether's theorem, so that's why these are important. So this one, as I said, was momentum, and that is spatial symmetry. So spatial symmetry. So these are related to the time and space symmetries, and that's why energy and momentum pop up quite a bit, because this kind of tells you how things evolve over time, and this tells you how they evolve through space. And so, yeah. Anyway, I'm getting a little ahead of myself here. I will see you in the next video.